Okay, welcome back. This is Chapter 2. Chapter 2 is actually a pretty small chapter in the book, so this ought to go pretty quick. It's about recursive algorithms. So what is a recursive algorithm? And so, no, it has nothing to do with cursing you twice. No, it doesn't have anything to do with that. What happens is there's a way you can solve a problem by just having a method call itself. Okay? That's all there is to do with a recursive algorithm is, when implementing it in a language, you would have, a method name called kumquat, and then inside kumquat, it would call itself. That's a recursive algorithm. The technique that we're going to be using is called divide and conquer, which means we have a big problem, and then we're going to start breaking it up into smaller chunks. And so often problems that kind of fit in that category are the ones that are recursive, where you do something over and over and over. So the whole point of divide and conquer is sometimes the problem is just too dang big. And you remember the tournament method where, two teams, and whoever wins that one, and then two teams over here and here, and then they get paired up, right? Okay? If you were to say, okay, here's 100 teams, who wins the Super Bowl? You'd go, I don't know. Because you have to go through the intermediate steps to be able to get there, right? Instead of having all the teams on the field at the same time, no, you only have two teams on the field at one time, and then you go from there. So it makes it small and easy to understand. When there's only two teams on the field, well, then it's fairly obvious who won and who didn't, right? There's only two teams, right? So it makes it easy to understand, and it makes the problem smaller. And then you move up and use the exact same technique again. And then you move up the tournament and you do it again. Move up the tournament and do it again. Okay. So another way of talking about recursive is what's called a recurrence relation. Jeez. They got some funky names here. The example they give is factorial. So I'm going to pop open Notepad. And so you guys remember how 5 factorial, right, is equal to, 5 times 4 times 3 times 2 times 1. Okay, remember that? Okay, good. So if I was to say n factorial is equal to n times n minus 1 factorial, okay? Isn't that really the same thing? Really? So 5 is equal to 5 times 4 factorial, and then 3 factorial. See how it kind of does a little loop there? Okay, so that's a recurrence relationship as described like this, which means this part, the factorial part, has to be substituted over here over and over and over and over again. Now, let's just say that I want to do this in an implementing language. Okay, there's more than one way of doing this. So not doing a recursive technique, I'm going to do public int. I'm going to call mine fact1 because we're getting ready to have another one. And so here we go. So basically I'm just going to do a for loop, right? So I'm going to have something like answer is equal to 1, and then a for loop that counts backwards, okay? Actually, well, yeah. So whatever this thing is, I'm going to say int I is equal to n, I is greater than 1, I minus, which means count back. If n was 5, it would go through 5, 4, 3, 2, 1. Got it? Good. And then I'm going to say answer is equal to answer times I. And then when I'm done, I'm just going to return the value of answer. Okay, now this is not recursive. It's just using a for loop. Cool. Now there's another technique using a for loop, and we'll explain that. So here we go. So I'm going to call mine public int fact2 int n. And this one's going to be kind of sort of simple, kind of. that basically says I want to return n times fact2 of n minus 1. Okay, remember how this formula right here, that's basically what that is right there. That's a recursive. Now, there's a problem with this, and is I need some way off the merry-go-round. Okay, so this will just go forever, and I need some way off. And so I need to have an if statement in here that basically says if n is equal to 1, then return 0. Actually, I got that backwards. If n is equal to 0, return 1. Okay, so this technique is using a for loop, and this technique is using recursion, so where it calls itself. This fact2 calls itself. So which one is better? Well, to tell you the truth, in this trivial example, I probably would not use recursion. I just wanted to show it to you so you understand what the consequences are, what the choices are. So to me, the first one probably would be better. Now, there are other types of problems that cannot be solved with a for loop and have to use recursion. Okay, so this is definitely something that we have to learn. I just wanted to show you that it's not the end all. Okay. Whew. On page 30, they talk about analyzing recursive algorithms, because you can kind of sort of tell it's a little complicated trying to figure out, how many assignment operators are there going to be, and how many, comparison operators, those kinds of things. So basically, you count the number of comparison and operators in a loop, right? And you count the number of times that the loop is going to run, which here, the number of times the loop is going to run is pretty doggone easy to spot. Here, you have to kind of think about it a minute, because it all depends on n, on how many times this thing's going to run. So there's an example on page 31 of trying to analyze a recursive algorithm. So here's one where this is kind of a generic thing. I don't even know what it is we're trying to solve. That's not relevant. This is just kind of a placeholder kind of a thing. So let's look at this for a minute. So what we're doing is there a simple way to solve the problem and jump off the merry-go-round? That's this thing. If n is less than or equal to some size limit, there's probably a direct solution. Like in the factorial example, it was pretty easy, because if n was equal to 0, just return a 1 and you're done, right? You don't have to do any recursion. So this direct solution is how to get off the merry-go-round, because recursion is no longer required. And then you need to break up the data into chunks. So divide the input into smaller pieces. And then after you've got them into smaller pieces, run the recursive routine over again using that thing. So let's say, I don't know, we broke this thing up into 10 pieces. And then we would just run that. And then when we got done, we would combine all the answers together. So there's a pattern here on how you would do a recursive algorithm. It's, I need off the merry-go-round. Is there a way to solve a trivial scenario without recursion? Break the input, recurse, and then put the things back together again. This is perfect for that tournament thing where I got 100 teams, but only 2 of them are going to be working at any one time. And so I just keep going and keep going and keep going. Okay, so if we were using the factorial example, again on the top of page 32, this is their way of looking at it, okay? So if n is equal to, I hate the way they do things. Remember in their pseudocode world, arrays started at 1 rather than 0, so this is dumb. And then otherwise, you get the answer, and there's a little bit more wordier than mine, but you get the point. Okay, so once again, does it meet that requirement? Is there a way off the merry-go-round? Yes, there is. Is there a way to break it up into smaller pieces? Yes, there is. There's a smaller piece, and therefore we do this, and then we turn things together. So there's a special type of instructions on how to solve the recursive algorithm efficiency. There's an acronym called REC. Of course there's an acronym, right? How to do this. And it's a complexity method. So for the little one, you get the amount of work done by the direct solution, and then the amount of work done by dividing the things together, and then the amount of work when you're combining the solutions together. And so this rec is the combination of all this stuff. Okay, so this is just a formula showing you how we just did what we just did. Okay. So that's the formula. And so one more time, if we were to look at this thing from a factorial example, here's what the factorial example would be using that technique where if the case is 0, well, I hate this. Anyway, and then how much work is here and then how much work is there, right? Okay, cool. So analyzing the efficiency of a recursive algorithm takes a special technique because some part of it is getting off the merry-go-round and some part is breaking it up, some part is doing the work, etc., etc., etc. Okay, so let's keep going. So a recurrence relation, ooh, how's that for a horrible term? A recurrence relation, page 35. So you've probably seen like an IQ test kind of a thing, where they say, they'll give you a series of numbers and say, what is the next number in the series? You've seen those things, right? Like, for example, here's one. Okay, so what's the next number? 5, 8, 14, 17. What it looks like, it starts at 5 and then adds 3. That's what it looks like. So let's just check it out. So 5. Yeah, okay, so I've solved this one. Starts at 5 and then adds 3. Okay? So that's a recurrence relation. Now, the way it's written out is like this. The first element is 5, and then the second element is whatever the previous element was plus 3. So that's the way you write out a recurrence relation. That'll work for anything. Now, the problem is, this is what's called, well, this is an easy way to look at it, but it's not an easy way to solve for a particular value. If I said, what is the 18th one, where n is 18, okay, then you'd have no immediate way to figure that out, would you? Not immediately. So we need to convert it to what's called closed form. Closed form is to convert this thing so that it can be shown. So there's an awful lot of good information. I like this website. It's got some slightly better ways of looking at it. So here is the closed form. So the closed form would be a sub n, whatever that is 0 plus d times 3. So in our case, I wanted to go to whatever. I wanted to go to 18. Then the d here is 3, right? So if I said, 18, this is the closed form, I could say, great. So it'd be 3 times 18 plus 5. Boom. All right? Kind of makes sense? Okay. Moving on. On page 40, they talk about approximating the order of recurrence. Now, this is really, really geeky. And I want to go ahead and get there, and then we'll talk about it in a minute. What this basically is saying, this is called the master method. Ooh, boy, doesn't that sound complicated? The master method. It's where A is represented by the amount of work required to divide the input. B is the number of times the loop will run. And F, I don't have an F, D, I guess, is the work that's happening inside the loop. So this is a technique for showing how you would calculate that. So you would do the amount of work, a big omega for this, and then for that, and then for that. So you kind of, n squared times log, and then n log squared times a. So that's the formula for trying to estimate what the recursion would be. This is the master formula. Dun, dun, dun. Okay, we're coming up on the 15-minute mark. This is probably a good place to stop before we move on to the next topic.